Welcome back from vacation. I hope you had an enjoyable, relaxing vacation. I hope so. So today we're going to continue with functions, but we're going to start a new idea called inverse functions. We're actually going to spend 2 days doing inverse functions. I'm going to take it nice and slow, and it will bring back hopefully a little bit of what we did the Friday before we left by reviewing composite functions for us. Your next exam is a week from today, Monday, and if you recall, it will go all the way back to class 9, which is the second part of section 1.6 and 1.7. So it will involve absolute value equations, linear inequalities. We didn't have that on our first test. Remember, 1.6 and 1.7 were 2 classes, but because of the snow day, we didn't cover the second part of that. So the exam will start with class 9. What on your schedule is class 9, which is the second part of section 1.6 and 1.7, and it will go through this Wednesday's class through 2.7, the inverse functions, and we'll stop there for the test. So today we're going to start inverse functions. Project 3 is due today. This was given to you the Wednesday prior to spring break, so if you haven't received this, please see me after class. You can either hand it in today in the blue folders or Wednesday. Okay, so let's take a look at inverse functions. Do you want to read this table for us, Chris? Okay, so what are we listing here for our input in this particular table? What's the input here? Right, so we have a table, and according to this function that we see below, the domain is the set of 6 countries that Chris just outlined for us: Brazil, Egypt, Germany, Iraq, Japan, and United States. And the range, so that's our domain, the range here is the literacy rate, which if you look at each of these, you can see that in the country of Brazil, 88.6% of the female population is literate. And that's goes up to the highest is 99 in both Germany and Japan. Okay, the United States is 97. So this is a set of ordered pairs that defines this function. Okay, the set of ordered pairs that defines that function. All right, so the idea that we're going to be working with for 2 days is this idea called undoing. And we actually have a sense of undoing from all the work we've done in algebra before when we've solved equations. But we're going to take a look at it a little differently today with this idea of this table, just initially, and then it will become more familiar to you in a little bit. So let's undo this function by interchanging the inputs and the outputs, or what we call the domain and the range for each ordered pair. So instead of inputting the country and getting out the adult female literacy rate, we're going to put in first the literacy rate. That's going to be our input, and then we're going to put the name of the country after it. So here we have the set of ordered pairs. We're undoing this function. Notice I'm not going to call it f anymore because it's a new function. So if I wanted to, I could call it g, and that's the undoing of f. Okay, I'm undoing f right now. And now you see that the domain is 88.6, 43.6, 99, etc. So my question is, here's a set of ordered pairs. Does the undoing of f produce another function? That's the question. Does it produce another function? In other words, is this undoing of f or this function called g, the set of ordered pairs, does that represent a function? Tyler says. Why not, Tyler? Right, right. So for the input of 99, there's 2 different outputs. And what are they, Tyler? Japan and Germany, right. So we know that for each input, in order to be a function, there can be one and only one output. That's how we define a function. It has to be unique. The output has to be unique for each input. Can't have 2 different outputs. Okay, so this is not a function. What do we call this when it's not a function? A set of any ordered pairs. It's not a function. What was it called? Going way back to the first day we covered this idea, section 2.1. I know it must seem like an eternity. Okay. If it's not a function, what's it called? A relation, right? So even though it's not a function, this is called a relation, right? Remember, a relation doesn't have that special condition that for each input there's one and only one output. It's just a set of any ordered pairs. Okay, so if a function f is a set of ordered pairs, and we'll call it xy, remember we could also call it x comma f of x if we wanted to, then the changes produced by f can be undone. So here's our original f up here. We can undo it by reversing the components of all the ordered pairs. So in other words, here we started with the country and the output was the female literacy rate. Now we're undoing that because now we start with the literacy rate and we're going back to the country. The resulting relation, y comma x, notice I'm calling this a relation, may or may not be a function. When you do that switcheroo, when you change the output and make it the input, and vice versa with the input and the output, you may end up with a function. Sometimes you may just get a relation. So we're going to look at this idea of undoing functions and their properties today and on Wednesday. So here's a function. Let f of t, we're going to also call it h, be this function right here, 6 plus 2t. What kind of function is that? 6 plus 2t equals h or f of t. What kind of function? What name would we give that function? Linear, right. So this says this is a linear function. So if I were to graph this, there's lots of ways to represent functions. This particular way to represent the function is an algebraic representation, algebraic or symbolic representation. We've looked at lots of these. We've also looked at the graphical representation. They all give us a different way of seeing the same thing. So a graphical representation. So let's take a look at the graphical representation real quick. We know it's going to be a straight line. What's going to be our input and what's going to be our output? What would be along the horizontal axis and what would be along the vertical axis? Someone want to help me with that? Independent variable, dependent variable. I'm looking at this equation. Or the table, you can see the same thing. So what would be our domain here? What's along the horizontal axis? What's the name of the variable? Huh? Yeah, days after the time, which equals the number of days that the seedlings have been planted, right? Okay. And what's along the vertical axis, Ken? Can you help me with that? Right, the height. Right, good. So this is the number of days that have gone by after planting. And this is the height in inches. So if we look at our equation, where does this plant start? At what height? Let's see. Look at this equation right here. At time t equals 0, which is when you initially plant it, right? How high is the seedling? 6. Notice this is the intercept right here, the vertical intercept, what we used to call y-intercept. In this case, it's the h-intercept. The order's just been reverse of the y equals mx plus b model. And then often in statistics, they'll start with the intercept first, because that's where you're beginning at 6. So when t equals 0, h, the height, is going to be f of 0, which is 6 plus 2 times 0, which is 6. So we're going to start right there, 0, 6. So initially this plant is 6 inches tall. So notice that this table in this function is only defined over a very explicit domain here. It says we're only looking at the height of this plant from day 0 to day 3, including 0 and including 3. We're not looking beyond that. So that's why we only have those 4 values in our table. How would I find the height after 1 day? Is there any way you can do it quickly without having to go through that whole formula from knowing some things about a linear function? One for 2, yep, that would be one way of doing it. And now we have 8 inches, so we have the domain 0, 1, 2, 3, and now we're up 8 inches, 1, 8. Now, is there a way to quickly go to 2 and 3 without going through the whole formula, Tyler? Yeah. Okay, so Tyler's saying that since our equation here, f of t equals 2t plus 6, we know the slope is 2 to 1. And if we look at our units, 2 inches per day. So it's going to grow 2 inches every single day. That never changes. That's what makes this a straight line. So it goes up 2 inches every single day. All right. So we know the next one has to be 10 inches and the last one has to be 12. So our final ordered pair here is 3 days. It's grown up 12 to 12 inches. From 6 inches, it's grown up to 12 inches. Okay, so this would be a graphical representation of that function. It starts at 0.6 and it ends at 312. This would be a tabular or numeric representation. Okay, so we've got 3 different representations going on here. We could also do a verbal representation if we wanted to. We can say this corn seedling started at 6 inches and it grew 2 inches every single day that went by. So if we want to write the ordered pairs for this particular function, notice your input is t and your output is h. Okay, so let's do the ordered pairs here. My first ordered pair would be 0, 6. My next one would be 1, 8, 2, 10, and then finally 3, 12. Okay. All right, so I'm going to change the next question a little bit. Suppose I wanted to know how many days it would take for the height of the seedling to reach 36 inches. How would I find t? I'm going to change that to 12. I want to keep it within this particular domain. Well, first of all, if you have all that table or that graph available to you, you just say, hey, I can just go to 12 as my output, and there's my answer, 3. So we know what our answer is already. But suppose I only had the equation, this original equation, f of t, h equals f of t, which is 6 plus 2t. Right? Or I'm just going to shortcut that, h equals 6 plus 2t. So I have this original equation, and I want to know how many days it would take for the height of the seedling to reach 12 inches. How would I find that answer? What would I do here? Bob? Yeah, plug in 12 for the height. Okay, so we could do that, but before I do that, we say that this equation, h equals 6 plus 2t, is solved for h. That's the language we used. This equation is solved for h. Okay, because it says h equals. Okay, the height is a function of the time. Now we're going to put 12 in for h. And now we're asked to find how many days it will take. So now we're going to solve this equation for t. So now we're going to solve it for t. I'm just going to, and to solve this equation for t, let's take a look at the steps. So over here, I'm just going to do something a little different. I'm going to start, this is my starting point now. I'm going to start with 12 inches, and I'm going to try to figure out how many days it's been planted. How many days it's going to take. So now I'm going to start with the height, and you're going to give me the number of days. Okay? So let's see how we get that. What would be the first step? Well, we're starting with the height, 12. And then what do we do? What would be the first step to solve for t here? What would be the first step to solve that equation for t? Minus 6, okay, from each side. So I'm going to start with 12 and subtract 6. All right, let me just, I want to make this a different color, just like we have over here. So this is my starting point. And let's see, what do we have here? 6 equals 2t. All right. Okay, so 6 is the result after I subtract 6 from 12. It's a single number, so I'm going to put that in parentheses like that. Okay. Someone else other than Kenneth want to help me the last step here? Sam? Divide by 2 on both sides. T equals 3. Okay. So our final result is the number of days. So in this particular equation, H is the input. The height is going in, and what comes out is the number of days. Okay, so we've interchanged the roles of the variable. Okay, in our original function f, right, in our original function we had t and then we had h as our output. In our new function, in this equation, g, h went in and the output was the number of days. So we've interchanged the roles. So how did we get h again? We took our input, we subtracted 6, we got a specific result, and then we divided it all by 2. So if we wanted to describe the function g of h, because now the input is h, we would take the height, we would subtract 6 from it, put it in parentheses, and divide the whole thing by 2. That's how we undid, how we got back to the number of days. Remember, f of t was 6 plus 2t. So here we have two functions, f and g. And g was able to take the output of f and bring us right back to the number of days. Now, this isn't anything new to you. In fact, I was looking at your faces. Some of you were sitting here and you looked so bored when we were solving this equation because you're like, what's going on here? I know how to solve an equation like this. I learned this many years ago. But what you need to be careful of, or at least aware of, is the idea that every time you solve an equation, you are undoing the operations that already happened. When you have this equation, 6 was being added to 2t. So you're undoing the addition of 6 by subtracting from both sides. Then t was being multiplied by 2. You're undoing. It's always by performing a series of inverse operations. That's what undoing does. Okay, and that's what we're learning, the basic idea for these functions. We're undoing what happened to them. So let's take a look at these two functions now. So here's our new function. Notice our new function is called g of h, because now the input is the height and the output is t, the day. So how much work do I have to do here to find these answers? How would I find the answer for the input of 6? How would I actually do that? There's a couple of different ways based on what we've done so far. How would you find the input, the output for h of 6? Some of you are doing it. Put h into the equation. Okay, so what is the equation? T equals g of h, which is h, 6, take away 6 divided by 2, which is 0. So my first ordered pair would be if I have a height of 6 inches, then that tells me it's the initial day that I've planted this, because now my input is the height and my output is g of h, or h comma t. Okay, so do I have to do this for every single one now, or is there anything above that will help me get the answer to the height of 8 inches, 10 inches, and 12 inches? Is there anything I can use from part A or B that will help me do that? All right, if not, then let's just keep doing it. How about when we have 8 here? What's my answer going to be? 1 day. How about when I have 10? 10 take away 6 divided by 2 is 2 days. So I've got, let's take a look at my ordered pair here. I've got 6, 0, 8, 1, 10, 2. And what would my final one be? We just solved that one. 12 inches after how many days? 3. Okay. So there it is. There's my set of ordered pairs. Okay. So do you see these particular outputs anywhere else in anything we've done today? The 0, 1, 2, and 3? Tyler? The first table. Okay, so let's take a look. Well, not the first table. It was the table for number 2. So look, in number 2, we had the time, and the output was the height. Now we have the height, and there's the same output. Okay. So the set of ordered pairs, big capital H comma T, is now over the domain 6, 12. So why did our domain change? Our domain initially was right here, 0 to 3. Why did our domain change? The input changed, right? Now my input is the heights. And the heights over those 4 days went from the smallest height was 6 inches up to 12 inches. So because my independent variable changed to the height, my domain had to change. So here's the ordered pairs right here, 6, 0, 8, 1, 10, 12, and 12, 3. Okay. So what I'd like you to do now is I'd like you to look over the functions f, which was the beginning of number 2, was defined for you, and the functions g. Talk about it at your tables, and just write down a couple of observations about these 2 functions. Whatever you notice, just write it down. Anything you notice. Everybody has at least one observation, so we'll start with table 1. Alicia, Paul, or Caitlin, you want to tell me one of your observations? Okay, they are reversed. Okay, they are reversed. Can you tell me a little bit about what you're referring to when you say they? Yeah. Okay, so if we're looking at the ordered pair for F, it would be time is the input and H is the output, and for G, it's HT. Okay, so we notice that the inputs and the outputs are totally reversed. Okay, they switch roles. Okay, table 2, what you come up with? Elena? They're both linear. Good. Both functions are linear. Good. Notice f of t was 6 plus 2t, and g of h was h take away 6 over 2. Now, that's not usually the form we look at a straight line. Notice this is the same thing as 1/2 h take away 6 over 2, or 1/2 h minus 3. So that would be how we would write that in our more familiar form, y equals mx plus b. Okay. Right, table 3, what you guys come up with? Right, outputs and inputs. So that's essentially outputs and inputs are reversed. That's similar to what table 1 came up with. Yeah, and that's a good addition. That even though you did your input and outputs and you reversed them, when you reverse them, you still ended up with a function. So both, Chris noticed that both f and g are inverse functions. Good. A lot coming out of this group. Table 4, anything else? The domain of f, the function f, is the range of g. So that's exactly the same thing, but just different language for what table 1 and 3 observed. They're just using a different language. They're using the language of function. They're saying the original domain of f, 0, 1, 2, and 3, is the output of our function g. It's the range of g. Okay? So what if I now put a little twist on this? The range of the function f, the range of f is what? Is the what? How could we continue this? The range of our function f, which was the heights, what is that in relationship to g? The domain of g, right? So the domain and the range of these two functions have switched roles. And I don't know if there's anything else you can add table 5. Did you come up with anything different than that? Okay, I'll start with you guys next time, okay? All right, so those are great observations. You did a good job on that. And the main idea here is that the two equations both are linear. And the big idea that actually probably table 5 noticed as well, the big idea here that you came up with, or the common idea, is that you noticed the switching of the inputs and outputs of the domain of range for these two functions. Okay, so if we now take a look at these two functions as we would write them algebraically, we call these functions inverse functions of each other. F and G are inverse functions of each other. The fact that G is the inverse of F is expressed by renaming G as F to the negative 1. Okay, we read F to the negative 1 as F's inverse. It's the inverse function of f. So, for example, instead of now saying f of x is 6 plus 2x and g of x is x minus 6 over 2, now notice I'm just using our normal notation of x. We're not talking about heights and domains h's and t's. So here's a linear function. Overall real numbers, x, it's just a linear function, and here is its inverse. So now instead of using two different letters, because this particular function has a very special relationship to f, it's its inverse, we use this new notation. So this says, whoops, my pen is actually a little off today. It's not going exactly where I ask it to go. So there we go. So we now call G the inverse of f. Okay. Now, what's really important is that, remember when we were using negative exponents, that had a particular meaning. It meant 1 over 3. It was the reciprocal of 3. F to the negative 1 does not mean, f of x to the negative 1 does not mean 1 over f of x. It has nothing to do with negative exponents. It's just read as, this is how we notate the inverse of a function. Okay, so we can say that G is the inverse of f, or we could say that f is the inverse of G. Doesn't matter. They're inverses of each other. So let's take a look at how this works now for just these two linear functions, as you noticed. Chris noticed that. Over any real numbers now. We're not in the situation where we're talking about the height of the seedlings. So let's find f of 10. So let's find f of 10. F of 10 is going to be 6 plus 2 times 10, which is 26. So if I wrote that as an ordered pair, if I would start to graph this, it would be 10, 26. Okay. Now let's find f inverse of 26. Can someone help me with that? F inverse of 26? Do you know what your answer is? 10. Did you do it by plugging it in, or how did you get the 10 so quickly? Chris, you said 10 right away. What did you do? You plugged it in. Okay, so you plugged it into the function 26 take away 6 over 2. Again, anytime you have a numerator where you're adding or subtracting, you're going to put that in parentheses, and that's 20 over 2, which is 10. So when you input 26, out comes 10. Tyler, you said 10 quickly. Did you do the same thing? No, what did you do? Okay, so there's a lot of language he's saying, but Chris noticed this. Excuse me, Tyler noticed that. He said, look, you've just told me that this new function is the inverse of f, right? That's what this means. F to the negative 1 means f's inverse. So when I put 10 into my first function and it comes out with 26, then I take that 26 and put it into my inverse, I got to come right back to where I started. That's what it means to be a function, inverse functions, right? So if we were doing this visually with our machines, our input and output machines, we're going to input 10 into our F machine, and out comes F of 10, which is also the number 26. And then we take that output, we take this output, and we put it into our F inverse machine, and out comes 10. We're right back where we started. Sometimes that's how we feel in life, right? We're not making any progress, all right? Well, these inverse functions, when we put them together in a sequence, we get right back to where we started. I like to refer to this as we just took a round trip. Hopefully some of you had a nice round trip vacation over the break. Okay, you just took a round trip. You started with 10, you did something to it, got 26, you put it in the machine, and you're right back to where you started. Okay, this idea of taking the output of one function and putting it into another function, what did we call that back on March? When did our vacation start? 14th, March 14th. What did we call that when we put two functions together in this particular way? When we took the output of one function and put it into as the input of another. What was that called? Composite functions, right? We composed the two functions, right? So we composed F and its inverse. Now we've just done that for a particular input and output. Let's do it generally. So let's do it for all x. So let's see how we would compose these two functions. This says f of f inverse of x. So in the f function, I'm going to put its inverse function. So everywhere I see an x in f, I'm going to put it in a different color so we can see it. I'm going to put in here now f of the inverse of f. Is going to go right into where I saw x. That's my new input. Okay. So what do I get here? 6 plus 2. Now what was f inverse of x? It was this whole thing called x minus 6 all over 2. So I've put x into my inverse function, and I'm looking to see what I get back when I compose it. Does anybody have a sense of what my answer is going to be? If I put x in to my inverse function and I take that result, I put my inverse function into my f function, what should I get back to? My original input. Here's my original input right here, x. Okay. So let's see what happens. We get 6 plus 2 times x minus 12 all over 2. I could write it that way, or I could just say 2 times x minus 6 all over 2, and the 2's cancel. However you want to do it. If you wrote it this way, it would be 6 plus 2x over 2 minus 12 over 2. Either way, you're going to get 6 plus x minus 6. Your 6's cancel, and you're right back to x. So you've done your round trip. Here's your input. You put that into your inverse function, which is f inverse of x. That's your output. And you put that into your f function, and you come right back to x. So you try this composition at your seats. F inverse composed with f of x. See if you can do that. Hopefully, you'll come up with x again, which is what, oh, I heard a bloop bloop. So a couple of different ways. It was nice going around and seeing how, oh, I just broke my glasses. Ooh. It was nice going around to see how you all approach this, and so I'm going to take some of the ideas I saw from walking around the room. So if we compose these two functions, to notice your first input is right here. You're putting x into the f function. So your first input and output would look like this, x, f of x. That would be your first input and your first output. Then you're taking f of x and you're putting it into f inverse. So you're performing two functions in a row, right? So let's take a look. What is f of x? F of x is 6 plus 2x. So this is what I saw on some of your papers. Some of you just replaced f of x with what it represents, which is 6 plus 2x. Just put that in parentheses. Think of it as just like a single value, like 26 or 10, just like a number. So now you say, okay, my inverse function is whatever I put into my inverse function, I subtract 6 from it and I divide by 2. That's what it says to do to my inverse, how I perform my inverse. So whatever I put in, 6, I subtract 6 from it and I divide it by 2. So f inverse of f of x is 6 plus 2x minus 6 all over 2. The 6's cancel. I get 2x over 2. I'm right back to x. So my round trip has been performed. Okay. So notice here that regardless of the order of how I compose these two functions, I get exactly the same answer. I get right back to my original input, no matter which order I compose these functions. So that is really a very big idea. And unfortunately, we had a week's vacation or 10 days in between our composite functions lecture and this lecture. So let's write that down. We notice that f composed with f inverse of x is the same as f inverse composed with f of x. Okay? This is a very big idea. Big idea. Like really big. Because we saw initially when we had any two functions, f and g, that the order that we composed them mattered. If we just have any old functions, f and g, the way we composed them, we got different answers. That's what we discovered on the Friday before vacation. It is only with inverse functions. This only is true that the order that you compose your two functions doesn't matter. It's only true when you have inverse functions. It's the only time. And that's how we define inverse functions. If we're trying to figure out if two functions are inverses of each other, then we compose them. We change the order of their composition and see if they both bring us back to x. If that's true, we know they're inverses of each other. Okay, so this is the definition of inverse functions right here, this idea here that how you compose the functions, the order that you compose these two functions does not matter, and they both bring you back to x. They both bring you right back to where you started. That's the idea of inverse functions. So that's something you want to have like big circles or stars around on your paper. Okay, so we're still working with this same function, or now we're changing functions. We're saying, here's f of x. Here's my input and here's my output. I don't know what my function is yet, or do I? Does that look like the same function we've been working with? Is this a linear function? Is the change in our outputs over the change in our inputs 2 to 1? These changes? Yeah. 2 to 1. All right. So we know our slopes too. So if I go backwards to 0, what would be my input? If I go backwards, 6. So this is exactly the same function we've been working with. All right. So we definitely know that this is a linear function. It's the same one we've been working with. So now if I switch roles here, if I put in my outputs as my inputs into my inverse function, I've got to come back to my original domain. That was the swapping idea that you all talked about. So the moral of the story is inverse functions just swap the input and output. Note that this means that the domain of our original function, the original domain, the top row here, becomes the range of my inverse function. And the range of my original function, the output, becomes the domain or input of my inverse function. They just switch roles. Okay. So here's the definition of inverse functions. This is taken right out of your book. If you compose G with F and you come back to X, and then you reverse the order and you come back to X, for every X in the domain of each function, then you know that F and G are inverses of each other. This is the really big idea. This is how you write it mathematically, okay? It's a lot of notation for this idea of coming back to the original input. So we've got a few things to look at here, and then I'm going to let you spend some time on your group activity. So let's, just like when we started out with functions, it's important to understand what inverse functions represent in stories and contexts and applications. So if we define our first function P to be a function of time, and we define it this way: if P equals f of t gives the population of Greenfield as a function of time, t, in years since 1900, what are the inputs, outputs in units? So how would I describe the inputs, outputs and their units? So what would be the input into this function? What would be the input? T. And what would be the output? Population, either f of t or p, right? So let's write it both ways. We could say t and f of t, or we can say t and p. Okay. Now, what about the units? We've taken care of the inputs and the outputs. What's the units for t, Caitlin? Right, so this would be years since 1900. Years since 1900. And what would be the units for f of t or p? What would be the units for the population? Number of people. Okay. Number of people. Okay. It's always a number. Okay. So once you have a problem like this, if you just write this down, it really helps you out quite a bit. So you know your input into f. Here's your f function. Your input is the number of years since 1900. You put it into your f machine, and out comes f of t, which is the population of Greenfield. Number of people. It's not in thousands, it's not in millions, it's just single individual people. Okay? So now it says, suppose we have this inverse function, f inverse 1400 equals 57, and we're trying to figure out what this means. One thing is you can just look at your original definition of input and output, or you can look at your idea of your function machines. So f inverse is going to take the output of your first function, which is the population, and bring you back to the number of years after 1900. So how would we interpret that particular notation right there? Does anyone want to give it a try as a sentence? Other than, oh yeah, Bob? Okay, hang on, I can't write that fast. When Greenfield, this isn't true data, by the way, had a population, yep, I got that, yep, 1,400 people. It has been 57 years since 1900. Okay, that would be one way to write it. Notice he used both numbers and their units. Okay. Or someone else might say in 1957, the population of Greenfield was 1,400 people. It's another way to say it. Okay. So what does the inverse function represent? What does the inverse function of f represent? Let me help you. If I ask you what the f function represents, the f function tells me the population of Greenfield at any particular time after 1900. So what would the inverse function represent? Since 1900? Right, so given the population of Greenfield, you can figure out where you are in time, the number of years after 1900, right? So look at your input. This always helps you write the sentence. Look at your input first, then your output. That helps you write the sentence. So my input is my population in terms of the number of people. And my output is the number of years after 1900. So once I figure that out, then I can write my sentence. My inverse function tells me that given the population, you can always start with given if it helps you to have a little structure. Given the population of Greenfield, if that's my input, I can determine the date or the number of years. I should say the year, determine the year, not the date. The year or the number of years after 1900. That's what my inverse function tells me, because my input now is the population, and what comes out, as Kenneth said, is the number of years after 1900. Okay? So I've done enough talking today. We can skip B for now and C, and, well, no, you try B at your seats, B and C. I'm going to check it off, and if it's okay, I'm going to, then you can start your columns and cell phones activity, okay? So you do B and C, and I'll check it out,